Hi, my topic of Termpaper is molecular chemistry in protoplanetary disk. We will go over why do we study the protoplanetary disk, what is a protoplanetary disk, the spectral regions we employ. This part will be studied in introduction. Then the disk structure, the evolution of water and deuterium chemistry, and finally some carbon chemistry. Why do we study about protoplanetary disk? Humans are fascinated by nature. They began asking questions concerning the origin of life, the origin of everything in nature, and so on since ancient times. However, they lacked the necessary equipment to investigate this at the time. But we have. We study protoplanetary disks as well as planets, comets, asteroids, and other solar system objects. We are attempting to piece together a picture of how the solar system came to be. What is a protoplanetary disk and how does it work? It's an accretion disk that forms in tandem with the birth of a star. T-Tauri stars and her big A or B stars are two examples of young stellar objects where it can be seen. The system's angular momentum is distributed across the protoplanetary disk while the mass is focused on the central star. Several hundreds of astronomical units are covered by the disks. The disk is the source of the solar system's planets, asteroids, comets, and other objects. Ground-based observations such as ALMA and space observations such as the Infrared Space Observatory, Herschel, Spitzer, and others are used to conduct observations. The region of electromagnetic spectra in the infrared and millimeter or submillimeter ranges is what we use. We examine molecules such as CO, CS, HD, and others using submillimeter and millimeter scales, also the disk's inner regions. We mostly study cold and warm OH and water molecules using far infrared. Oxygen fine structure lines in 63 micrometers, 145 micrometer, and 158 micrometer are also available. Lines of neutral carbon can also be seen in the spectrum. We see water molecules, OH, CO2, and other gases in the mid and near infrared. Infrared radiation is emitted by aromatic and aliphatic carbon molecules when they bend and stretch. As a result, we can investigate carbon molecules in the infrared range. However, due to the presence of dust particles, the disk will be optically thick for infrared. As a result, we don't have much information regarding carbon compounds in the disk inner area. However, for millimeter and submillimeter regions, it is optically thin. As a result, we can use it to investigate the inner regions. In this table, we can see the spectral region corresponding chemical transition that correspond to the particular radiation and the quantity we are interested in. The main wavelength we using are infrared and submillimeter. This coming from the rotational and raw vibrational. Almost all transitions are rotational and raw vibrational transitions. And the main quantities we are studying is temperature, density, ionization, photochemistry, etc. Let's have a look on the disk structure now. The cross section of the disk is depicted in the diagram. Near the star there are some area where the chemical components are scarce. The reason for this is because the photons from the star will disintegrate the molecules. This region stretches up to 0.1 astronomical units. The disk containing a variety of chemical substances begins after this section. There is a hump that we can see. This is due to the dust particles present. At the front end of this, the temperature is roughly 1500 Kelvin. In this location, a large portion of photons will be absorbed. This disk will be divided into three zones from this point, based on the distance from the disk central plane. Color coding on the right side allows us to see it. Photons are scarce in the region central to the disk plane. As a result, that area is extremely frigid. In this region, chemical substances are mostly condensed in condensed form. In addition, dust particles have a natural gravitational attraction to the core disk. As a result, rocks can form here. In comparison to other places, the red colored zone has a higher temperature because stellar light are absorbed in this region. As a result, this is a photon dominated zone. This area also prevents photons from reaching the lower sections. This refers to yellow areas. However, certain photons, including cosmic ray photons, will arrive there. As a result, the yellow region appears to be a region with a lot of molecular chemistry. In this area, a large number of compounds are formed. A blue mark may be seen in the left hand side. It is known as the snow line. The temperature is around 150 Kelvin here. Water, ammonia, methane, carbon monoxide, carbon dioxide and other volatile chemicals condense into ice grains here. The blue region on the right side begins after the snow line, as can be seen. Temperature, density and other factors influence the location of the snow line. It was between 2.2 and 3 astronomical units in the solar disk. There is also the asteroid belt to consider. Beyond the snow line, giant planets emerge. Prior to the formation of the snow line, terrestrial planets exist. These figures show the distribution of dust temperature, gas temperature and gas density. We can see that the gas density is higher near the plane of a given R. As you move away from the central plane, it lowers. The temperature of both the gas and the dust is rising as the plane moves away from it. When we travel along the radius, we may see a similar trend. Along the radius, the density of the gas decreases, as does the temperature of both the dust and the gas. The ratio of dust and gas densities is depicted in this image. The ratio is large near the disk plane, as we can see, marked with the red color. That suggests there is a lot of dust there. As we move away from the plane, the ratio diminishes. This demonstrates the tendency of dust to settle into the disk plane. Now let's talk about the water on the earth. There are primarily two reasons that can be used to explain how water is delivered on earth. The water is provided in one way by hydrosilicate. The argument against this is that the low water content in hydrosilicates due to the low water content in anhydrous meteoritic silicate and the non-detection of hydrosilicate spectral characteristics in infrared disk spectra. The second idea is that some types of comets and asteroids supply water. This argument was based on research into Debye ratio and comets. We already knew that the chemicals would condense at a great distance from the star. That's roughly 200 astronomical units. At 1 astronomical unit, water can be formed in the form of vapor. As a result, the probability of forming water here and having it accepted by the earth is reduced. As a result, we can conclude that the water developed in other places and was carried to earth by objects capable of traveling here. Comets or meteoroids will be the culprits. We are looking into it by comparing it to the Debye ratio of ocean water, known as standard mean ocean water or SMO, and the Debye ratio of these things. The range of Debye ratio of meteoroids and interplanetary dust particles in these figures crosses with SMO. Jupiter's Debye ratio is comparable to the value of interstellar medium. The same is true for Uranus. The value of comets is high by some factors of SMO. As a result, we cannot assert that the water is provided by comets. The water is also said to be provided by meteoroids, according to the argument. However, as shown in the image, the values are distributed across a range. As a result, this argument is inconclusive. At different temperatures, different methods of forming water molecules are used. Water molecules are generated by two neutral processes above 300 Kelvin. One oxygen atom combines with one hydrogen molecule to produce one hydroxyl molecule and one hydrogen atom. One water molecules and one hydrogen atom will be generated when the hydroxyl formed in this stage reacts with another hydrogen molecule. However, below 100 Kelvin, ion neutral interactions occur, resulting in the formation of water molecules. When H3 plus comes into contact with the oxygen atom, it forms H3O plus. It will be followed by several dissociative reactions which will result in the formation of H2O. The temperature is extremely low in the midplane. As a result, the water has frozen into dust grains. We know that water has two states of spin. The first is ortho, which has a spin of 1, and the second is para, which has a total spin of 0. The ortho to para ratio is 3:1 in degeneracy. This value should be obtained at high temperature limit. However, at equilibrium dust temperature, water production in cold grains causes this ratio to be lower. Ortho to para or reverse transition is not possible. Only chemical reaction is the way for this transition. So from this we can say that the water molecules were formed in cold region. In the IR measurements, there are fewer evidence of water in the disks around Herbig A or B stars than T Tauri stars. This is due to the high quantity of photodissociation that occurs in Herbig A or B stars. As a result, water molecules will soon be separated. We can observe from the above graph that the d/s ratio of ISM is substantially lower than that of comets, meteoroids, and other objects. Isotope exchange reaction is the case behind this. It works at temperatures ranging from 10 to 30 Kelvin. A reversible reaction can be seen here. When H3 plus reacts with H3, it releases energy equal to 232 Kelvin. So, in order to get the opposite reaction, we must give the same amount of energy. However, we are not obtaining that in this circumstance. As a result, according to the Le Chatelier principle, only one direction of reaction occurs. As a result of iron molecule reactions, H2D plus will accumulate and transfer into other molecules. The reactions shown here are applicable in the temperature range of 70 to 80 Kelvin. It is also important for the inner warmer disk region. We can observe that the deuterated chemicals are accumulating here as well. Deuterated molecules are also involved in subsequent processes. Recent comet research indicates that the d/s ratio are derived in part from the parental molecular cloud and in part from the disk. However, we had seen the reactions described above. More deuterated chemicals are accumulating there. That means these items have lost their d/s history. As a result, using the d/s ratio to discern between contribution from prestellar chemistry and disk chemistry becomes more difficult. Let's have a look on organic molecules now. The large molecules are mostly made up of 4 elements: carbon, hydrogen, oxygen, and nitrogen, or CHON for short. Glycine was identified after several complex organic molecules were detected in cometary dust particles analyzed by the Giotto probe in Halley comet. This suggests that the comets could have biologically diverse nature. The presence of deuterated amino acid in meteoritic materials indicates that they developed in dense prestellar molecular clouds under cold and dark conditions. Endothermic processes produced complex organic molecules during planet formation from CO, N2, OH, and H2. Following their production, they can be dissociated by star photons or cosmic ray photons and return to the gas phase. It can also create ice and collect. Turbulence in the disk is also important in the evolution of molecules. It results in the mixing of several complex organic molecules, resulting in a diversity of organic molecules. Fischer-Tropsch catalysis can produce hydrocarbons from CO and H2. The Haber process can also produce ammonia molecules. Both of these reactions occur in the presence of metals. We know that spongy iron is used as a catalyst in the Haber process. The efficiency of this process is determined by the characteristics of metallic surfaces. We can say that these processes occurred efficiently on Earth or elsewhere, resulting in the development of life on Earth. These studies are all inconclusive. The main reason for this is that we will not receive radiation from every point of the disk. As previously stated, infrared from the disk center will not reach us. Another consideration is detector sensitivity. We can only hope that more sensitive detectors will arrive in the future to solve these issues. The recently launched James Webb Space Telescope can disclose a great deal about this. So that's all about the presentation. Thanks for listening to me.